But because of that, if I can, because of the Veterans Day celebration thing, I will let you out a little early if I can, so you can get down there if I can. But basically, what we are talking about today is we're going to go over some review questions, okay? For chapters 8 and 9, that is your final exam. It does not include anything else, but to be able to do 8 and 9, you definitely have to have a good understanding of the chapters that came previously, okay? But what I need you to get solid in your head is what types of problems you're going to be looking at on the final exam. So I put it on this page. It's in your guided notes book. Look at the beginning of Module 4, and it's page 2, and it says 8 and 9 notes. And it tells you, first type of problem is going to be confidence interval. Okay, you know that that's not necessarily the first type of problem on the test, but still, you'll have confidence interval problems. One thing that you need to remember about confidence interval problems is we're always going to take alpha and divide it by 2. Okay, that's an important point. Now, with those problems, you've got 3 different subtypes of problems, if you will. You've got 3 different ways it can go. You can have population standard deviation given to you. If you have the population standard deviation given to you, then that's one calculation, one thing you need to remember. If you don't have the population standard deviation given to you, then you have a sample standard deviation that you have to use. And the next thing is proportion problems. So 3 types of problems, 3 types of confidence interval problems. Everybody understand that? Next thing is going to be types of problems that find the sample size. Now, there's only 2 types that find the sample size. One, we're dealing with population standard deviation given to us, and the other one is a proportion problem. Now, why don't we have sample standard deviation? Because we're trying to find the sample size, so this is before we have taken the sample. Make sense? So what we have to do is have a population standard deviation, or they may say something like, the preliminary sample gave us a standard deviation of such and such. Well, that's what you use because that's the only standard deviation you have. So it's either that type of problem or it's a proportion problem. So you got 2 types of sample size problems, and you have different formulas for them, of course. And then the third one is our Chapter 9 stuff. Now, this is hypothesis testing. Hopefully you have made it through that really terrible video that I made for you when I was at home. Did any of you, and I apologize because I sounded horrible on it, but that's the best I could do. Because this cold just will not go away. It's not, fortunately, I'm going to tell you, it's not COVID. I tested negative, so I just have cold, right? I have 5 grandchildren, and they're wonderful and have the most incredible hugs, and they carry vicious viruses with them everywhere they go. So that's my excuse, all right? So anyway, 3 types of hypothesis test problems. 1, we know the population standard deviation. 2, we don't know the population standard deviation. We must lean on the sample standard deviation. And 3, proportion problems again. Now, these numbers that are here are part of the final exam practice questions that are in the back of your guided notes book. And that's where we're headed today to do some of those. I'm going to do one of each is what I'm going to do. I'm going to do one of each type of problem and try to help you understand. But do you understand that I've put here the numbers of the types of problems that they are? In other words, number 8 through 12 in that review is confidence interval with the population standard deviation. You should go to this list to make sure you know what type of problem you're hitting, okay? Because you should know it from the problem type, but if you don't, this will teach you. All right, so that's what that page is all about. This page is the first page in that guided notes module. And what I tried to do here was to kind of give you a side-by-side comparison of the differences of the formulas that are involved in the different types of problems, okay? So I want to go over it just really quickly, because if we're dealing with confidence interval, we're dealing with some of the same stuff, and when we hit, with population, some of the same stuff, and some of it's different, okay? One thing you should note is that population standard deviation problems and proportion problems always use the Z-table. Sample use the T-table. If you use the wrong table, you'll miss it, okay? So you're going to have that settled in your head. Now that carries through for the hypothesis test problems too, okay? Of course, when you're doing sample size, you're always using the Z-table. And maybe that'll help you just to see it side by side. The other thing you have to keep in mind is we always have to adjust the standard deviation. Remember in chapter 6 and 7, when we had a problem that used the standard deviation, we used the standard deviation to calculate the z-score that we were using, right? We didn't divide it by the square root of the sample size. If it was population, we just used it. Not in these chapters. So from now on, whenever you have a standard deviation given to you, whether it's sample or population or one you created from the proportion, you've got to adjust it. But I'm going to try. So there's an adjustment that has to be made. What are you doing to it? Well, you're going to take it, whatever is given, sample or population standard deviation, and you're always going to divide it by the square root of the sample size. You see it? What do you do for proportion? Well, proportion is quite different. It takes the square root of p hat times q hat divided by n, and that works for the confidence interval. But for the other two, what is it? For the other two, you're not using p hat and q hat, you're using p and q. Why is this important? Because in this type of problem, hypothesis testing, you will have both p and p hat given to you. Are you with me? You've got to use the correct one to calculate the standard deviation, okay? How do you know if you get confused and you don't have this page? Look at your formula sheet. It's on there. So please, please check your formula sheet, especially when you're calculating standard deviation if you get confused about which one to use, okay? All right, have I said enough about it? You want to just work some problems? The other thing that this is going to tell you here is this, and hopefully you got this from the video too, the videos that you've listened to. When we have hypothesis test, we basically have three different types of tests that we can do. First, they're going to say, is the current population mean different from what it used to be? And guys, don't kid yourself. The question is always about the population mean. It's never about the sample mean. If we wanted to hypothesize on what the sample mean was going to be, we'd simply take the sample and calculate the mean. You following me? The hypothesis is about population data. I'm giving you the answer to test questions if you are listening carefully, okay? Because I've just gone through your final exam twice, worked every version of it, and I want you to be familiar with these concepts. It's not all working problems. There are some conceptual questions that you need to be able to answer. One thing is, if you are dealing with a hypothesis question, what are you trying to hypothesize about? It's never about sample data, it's always about population data. What are we trying to estimate? We're trying to estimate what the population mean is, what the population proportion is, not the sample. If we wanted that, we would simply take the sample and calculate it. Does that make sense to you? Okay, nod, so you're following me a little bit. So you have three different types of tests. The population mean is not what it used to be. That's the first one. It is a two-tailed test. For this test, we must divide alpha by 2 and split it and put half of it in each tail. For this test, when we calculate the p-value, right, the p-value that tells us whether p-value is less than alpha or not, we must calculate it for one tail and then multiply it by 2, okay? That's that first one. The second one and the third one are simply left-tailed and right-tailed tests. Now, a left-tailed test is always going to have a critical value. This critical cutoff value is what this line is. The critical value for z or the critical value for t, doesn't matter which one it is always going to be negative. Why? It's on the left side of the curve, okay? For a right-tailed test, the critical value, the cutoff for t or z is always going to be positive. Now, where does the observed value for z or t fall? Well, that's up to the sample. It'll fall either into the rejection region or it'll fall outside of it, and that's how you make the decision. You also can take that observed value for z or t, and you find the area in the tail of it. Doesn't matter which tail you're looking at a tail on this side or a tail on this side. You find that area, that's the p-value. If p-value is less than alpha, then you can reject, okay, the null hypothesis. All right, one more thing before I get off of this, okay, because concepts are really important in this thing. Okay, now I forgot what I was going to say. So bad. I'll remember it later, okay? God, this cold will not let me go. All right, so let's do some problems. I want you to do this. Now, I know this is the problems we're going to go over. If any of you have phones and you want to take a shot of this, you can. If you don't, and you want to do it later, I'll leave it lying up here so you can get a shot of it later, okay? Because I didn't make copies of this for you today. I expect you've got paper, and we're going to do it on paper, okay? First, know Chapter 9, page 4 in your guided notes book. Put a star by that page. You need to know how to state both the null hypothesis and the alternative hypothesis. This is the point I was going to make a minute ago. Which one do you state first? You always state the alternative hypothesis first, okay? You always state the alternative first because the alternative hypothesis is the reason you're doing the research. The researcher has an idea. I don't know if you got this from my lectures. I'm sorry if I'm going over stuff multiple times with you, but that usually doesn't hurt you. The researcher has an idea. His idea is stated in the alternative hypothesis. It's always going to be greater than, less than, or not equal to. Those are the only operations that will ever be in that alternative hypothesis. The null is the opposite of the alternative. Okay, so everything that's not included in the hypothesis 1, the alternative, is included in the null. Now, how do you make a decision? Well, you never make a decision about the alternative hypothesis. You only reject or fail to reject the null hypothesis. It's just the way it's done. I know it's kind of confusing and it seems a little backwards, but that's what we do. And if you go back to that illustration that I gave you on page 1 in Chapter 9, this is incredibly important. I would say there are at least 3 questions on the final exam that are going to be focused on this, okay? So put a star by that one too. And what it's saying is, what is a type 1 and a type 2 error? Well, a type 1 error is, in my mind, the worst error you can make. Guys, it's the one that I illustrated for you like this. It's sending an innocent man to jail, okay? It's rejecting the null hypothesis when it shouldn't have been rejected. That's a type 1 error. And you also need to know this. A type 1 error is equated to alpha. It's considered the alpha error, okay? So we equate that to the alpha. The alpha is the probability of creating a type 1 error, okay? I've told you a lot in a short amount of time. If you didn't get the notes on it and you want to go back and listen to this again to write the notes down, you certainly can. And now let's go into some problems. These are the problems I'm going to hit, and if you want to follow along in your guided notes book, we're going to do confidence interval problems first, and we're going to hit 8 and 10. See if I can find them. I used to have page numbers on these things in the book, and then the page numbers would not print correctly, and I had to take them off because I was merging too many different types of documents together was the problem. So anyway, it's the final exam practice questions. The very first one is what we're going to work on first, okay? So it says I have a sample size of 97 from a population that has a standard deviation of, a population standard deviation, you know your symbol, equal to 7, and it gives me a mean of 47, okay? Are you there, everybody? See where I am? Okay, we want a 99% confidence interval for the population mean, and we want to round it to 2 decimal places. So what did they tell me in this problem? Well, they told me they had a sample size of 97, and they told me the population standard deviation was 7, okay? They told me that they took that sample mean, and it was 47. The sample mean produced a mean, okay? I mean, the sample size 97 produced a mean. That's the sample mean, and that's always what you're going to look for. And then they said, confidence interval, want 99%. I'm going to put that down as a decimal, okay? Now, immediately when you start this, here's how you do it. You say confidence interval is 99, alpha is equal to 1 minus the confidence interval. Got it? And confidence intervals, I always divide alpha by 2. So what I'm going to be working with is 0.005. That's the area that I'm going to be working with. Do I look it up on the Z table or the T table is my next question. Well, look, standard deviation of the population is given to me. I've got a Z-score. So I go to my Z table. I'll get everything organized in a minute. And on this test, you never have to use the positive side of the Z table, okay? You're always going to be looking things up in the tail. And if we're always looking things up in the tails, we're going to use the small side, which is the left side, which is the negative side. So I go over here and I go 0.005. I don't find it. Where is 0.005? 005 up here. 0.05149 is right here. I could call that 2.57, or I could call that 2.58, or I could go halfway in between them, and you'll be okay either way, either of those choices, okay? So I'm going to kind of go with 2.57 is my Z-score, okay? Now, I'm going to do the calculation for confidence interval. If you go back to where you've got these calculations, what is it? Well, it's the margin of error plus or minus Z times the standard deviation of X bar. In other words, what's the first thing I've got to do? Adjust my standard deviation. It's not 7, it's 7 divided by the square root of the sample size. I'm going to cover so much today, I'm going to depend on my notes to help me with this, so just give me a minute. You've got these actual notes in the back, okay? But I'm going to change this and say I used 8, because that's what I used, and it'll change our calculations just a bit, not much. Not to make you miss the problem, all right? So next, I say, let's figure out what the margin of error is. It's going to be Z times the, I got to do this one, sorry. Standard deviation came to 0.7107. And go to 4 decimal places with all of your standard deviations, okay? You should be okay. I've just, like I said, worked through all the versions of the test, and I was okay with 4 decimal places. And I'm going to multiply that times that adjusted standard deviation. So what I came up with was my margin of error is 1.8336, all right? Now, how does that work? Well, the confidence interval is equal to the sample mean plus and minus, or minus plus and minus the margin of error, right? The confidence interval is equal to, what's the sample mean? 47 plus and minus the 1.8336. So you say 47 minus 1.8336. Well, let's go to 2 decimal places, because that's what this one rounds to, and just say 47 plus 1.83, and I get 40, or minus 45.17. And when I add, I get 48.83. And that's my confidence interval for that one. So understand what it's asking, or what you're telling it that you have, okay? You are 99% certain. You understand what I'm saying? Pay attention to what I'm saying. I'm 99% certain that the population mean is between these 2 numbers. Okay? That's valuable to know. I'm 99% certain. That's pretty good, isn't it? Are you good with that? Let's do another one. Let's do number 10 on this one. I'm hoping to make it through your class, because if I make it through your class, I might have to post a recording for the next class, because I might not be able to talk. Let's do 10. It says we've got a random sample of 82 customers. They visited a department store. They spent an average of $71. And they suppose the standard deviation of expenditures at this store is, and they gave a population standard deviation of $19. And they want the 98% confidence interval for the population mean rounded to 2 decimal places. You do it, okay? I'm not working this one for you. you should be able to work this one, okay? Try not to go to the hints in the back of the book. Try to do this one doing just exactly what we did. Write down what you know from the problem, and then work it. And then if you make a mistake, it's better to do it in this class than it is when we come back for the final. So there'll be hints up here if you need them, okay? Okay, solution. They said they had 82 in the sample size. They had a standard deviation for the population of 19, and the sample mean came out to be 71, and they want a confidence interval 98%. So automatically I say, well, alpha is 1 minus 0.98 or 0.02. Divide it by 2 and I get 0.01, and when I look in my z-table, I got 2.33 for my z-score. I realize it's negative, but when we're doing confidence intervals, we just need the positive z. Okay? Good so far? Adjust the standard deviation. Take that 19 and divide it by the square root of the sample size and go to 4 decimal places. Okay? And now, take this times the z, multiply them together, you have the margin of error. And what you're going to do is take the confidence interval, you're going to build it around the sample mean, which is 71. You're going to say 71 plus or minus, and whatever that number is, we're going to go to 4 decimal places with it. I got, see if I find what I got, 4.89. Said go to 2 decimal places with it, it's what I meant to say, okay? So when I add and subtract it, what do I get? Well, I get the lower number is 66.11. The higher number is 75.89, and that's my confidence interval. What is it telling me? I'm 98% certain. That's how confident I am, okay? Did you guys have a question? Are you okay? Or do you have a question? Okay, I'm 98% certain that the population mean is between these two numbers, okay? Is there something I can answer for you rather than finding it on your phone, maybe? I'm sorry? Oh, okay. Okay, so what did I say? So I'm 98% certain that the population mean that I get is going to be between these two numbers, okay? Got it? That's what it's telling me. All right, population standard deviation is the last two, the next two problems are going to deal with the same thing, except it's a sample standard deviation. Now this should say to you, sample standard deviations mean that we have to use the t-table, right? So that's quite different for us, and those are the only ones we really have to watch out for is sample standard deviation. Now, I want to note one thing. Listen carefully to what I'm going to tell you. How do you know to use the z-table? Well, you're given the population standard deviation. How do you know to use the t-table? Somebody tell me. Be brave. Come on. How? Say it again.
There's no standard deviation, use the t-table?
Well, if there's no standard deviation, it's a proportion problem, so you got to use the z-table again. That's a good point. I'm glad you brought that up. How do we know to use the t-table? Yeah. Okay, that's a good point. If you're using the t-table, you're given the sample standard deviation, right? You have to. What if you're given both of them, guys? What if it says, you know, I've got the population and I've got the sample standard deviation? Which one are you going to do? Which table? Z, yeah. Z is more accurate. Z is the way we go. Was that a guess? It's okay. Okay, now listen. What did I just say? If you're given the population standard deviation, use the z-table. No exceptions. If you're given the sample standard deviation, you might still use the z-table because you might also have the population standard deviation. So what is my rule for when do I use the t-table? Yeah. You absolutely do. You have to use degrees of freedom when you use the t-table. But how do I know? How do I know that I have to use the t-table? Okay, I'm going to nitpick, but this is important. You're not given the population standard deviation, okay? If I'm given both, I'm going to use population. But if I'm not given the population standard deviation, I use the t-table. Did you hear what I said? There's a question that everybody always misses on the next test that I should have just cleared up for you if you were listening, okay? So that's what I want you to get in your head. If I'm given population standard deviation, I use it. The z-table is much more accurate than t. You know, go to the history of the t-table. I gave you a little bit of that in the video, and you'll see why. But if I don't have the population standard deviation, they have to give me, I have to get a sample standard deviation. I might have to calculate it on my own. That's how I know to use the t-table. I was not given the population standard deviation. Did you say that to me a minute ago? You're not, you know, you said you're not given a standard deviation at all, right? And if you're not given anything, well, it's a proportion problem, right? Okay? Are we clear? Is it about as muddy as it gets? Listen to this part of the tape again, okay? I get clearer as you listen to me more times. All right, let's talk about problem number 18. Okay, in 18, this one says, I have a sample of 20 elements, and these sample produced a mean of 91.4 and, look at this carefully, and a standard deviation. The sample produced the mean and the standard deviation, sample standard deviation, right? Assuming it has a normal distribution, which that's fine, the 90% confidence interval for the population mean is, all right, so let's write down what we know. We know the sample size was 20. We know the sample mean was 91.4, and we know the sample standard deviation. Use the right symbol, okay? The sample standard deviation is 11.16. We are wanting a confidence interval that is 0.90 or 0.9, and now we do, a lot of the stuff is exactly the same as we've done before. We kind of got to say, what's alpha? Well, alpha is 1 minus 0.9. And what's alpha divided by 2? Because it's a confidence interval, that's going to be 0.05, isn't it? What do I need? This time I need the t-table, okay? Now, if you're not used to using the t-table, you've got to have degrees of freedom, okay? So you got to go back. If I have to use the t-table, I got to find degrees of freedom. This one is 19 with an area of 0.05 in one tail. How do I know it's in one tail? I divided alpha by 2. So I'm going to go to 19, and I'm going to go over here to where it says level for a one-tailed test of 0.05, that column, and I'm going to get 1.7291, okay? This t-table has changed on us since we changed publishers, so give me a second to make sure my notes are still right. Okay, it only had 3 decimals, and this one goes to 4. What did I say it was? 1.7291, is that what I said? Yeah, okay, so that's good enough. So t is equal to 1.7291. You may find that you're a slight 1/1000th off when you get these answers, depending on whether you're using your calculator or the tables to calculate z and t, but you will be close enough that you will find the correct answer, okay? There won't be any doubt in it. Now I've got to do standard deviation adjustment. I have to take 11.16 and divide it by the square root of the sample size, which is 20. And when I did that before, let's see what I got. I got 2.4955. All right, confidence interval. This time, my confidence interval is going to be equal to the sample mean, which is going to be 91.4, plus and minus the t-score of 1.7291 times that standard deviation 2.4955. These two multiplied together give me the margin of error. Thank you. Good. Okay, that's my margin of error. I'm adding and subtracting my margin of error from the confidence interval. Now, what I ended up with, let's see, maybe slightly off. I don't think so, though. I ended up with 91.4 plus and minus 4.31, and that came out to be 87.09, 95.71 is the high, okay? That should be really, really close, even though this extra decimal place, if you're looking at my notes from the guided notes book on it, may be slightly off because when the previous publisher that we used did not have the t-table go to 4 decimal places. It won't be off by much. Okay, it's the same way. Now I want you to work the next problem, okay? See if you got this. Number 20 is your next one. I'll put it up here just in case you don't have your guided notes book. If you don't, you're going to have trouble anyway, aren't you? Number 20. Random sample of 23 tourists who visited Hawaii this summer spent an average of 1456 with a standard deviation of 263. Talking about samples, so it's the sample standard deviation. It has a normal distribution spent by all tourists, and they want a 95% confidence interval for the amount spent by all tourists rounded to 2 decimal places. Okay? Same exact thing we just did. Okay. Solutions here. Solutions also in your guided notes book. I know you know that, but I just want to put it here so that you can sort of see it. Of course, we do the same things. We adjust the standard deviation. We calculate the t-score based on degrees of freedom and alpha divided by 2. And this one goes to 4 decimal places in this table. So when I multiply these two things together, standard deviation adjusted and the t-score, I get the margin of error, which I add and subtract from the population, the sample mean, right? So I get the range. They're 95% certain that these people spend between 1342.26 and 1569.74 on every Hawaiian vacation, is what that would interpret to. Any questions on that? Since I'm running late, if you don't, stop me if you have questions, okay? But we need to go on to proportion problems. So we got a proportion. Which one did I say I was going to do? Lost my piece of paper. So let's go to number 23 for the proportion problem that we look at first and see what difference it has, okay? So number 23 says, there's a random sample of 450. It produced a sample proportion of 0.71, and they want a 95% confidence interval. I usually get a bunch of emails about this time in the course saying, how in the world do they expect me to answer this question? They didn't give me enough information. Please note, no standard deviation, right? No standard deviation. If that happens and you see a no standard deviation problem, check and see. It's probably a proportion problem, okay? Proportion, it says sample proportion, so this sort of helps us out a little bit. So anyway, when I'm setting up number 23, what I say is there's a random sample of 450, and it gave a sample proportion. Now I have sample proportion is p hat, okay? P hat is 0.71, and I want a 95% confidence interval. Okay, for the population proportion, they want to go to 4 decimal places. Because proportions have so many decimal places, we usually go to more decimal places with it, okay? I'm going to work this one, and probably not going to do a second one with you, so just pay attention as we go along with this. We must have a standard deviation to work with. How do we get it? Well, we were only given the sample proportion. Now, if the sample proportion, p hat, is equal to 0.71, what's q hat? How would I get it?
1 minus 0.71.
Exactly, 1 minus 0.71. So for this one, q hat is going to be 0.29. And that's what I'm going to use to calculate the standard deviation of the sample proportion, okay? I'm going to use the square root of p hat times q hat divided by the sample size of 450. And when I did that, be sure you go to 4 decimal places, okay? Because proportions have so many decimal places. Good? I'm good. I've got the standard deviation I need. Am I using the z-table or the t-table, guys? Z-table. Proportions always use the z-table, right? So let's go with alpha is equal to 0.05. Alpha divided by 2 is equal to 0.025. And that's where I get my z-score. And my z-score for this one, 1.96, is one I've looked up many, many times, so I happen to know that one. How's the confidence interval? Well, it's going to equal the sample proportion plus and minus the margin of error, which is calculated the same way. The z-score times the standard deviation that I adjusted. I get that to be 0.71 plus and minus 0.0419. It said go to 4 decimal places, so I'm going to keep all 4 of those. And I get 0.6681 and 0.7519. Sometimes they want me to represent this as a percentage. And if they did, I would say between 66.81% and 75.19% of the people did whatever we were checking on, okay? What was it this was about? Doesn't say. I would say it's between 61.81 and 75.19%. But don't do it unless they tell you to, right? You're a multiple choice final exam, so you'll be able to tell what the format needs to be. And that is all of your confidence interval problems. I gave you another one, which is number 24, which we won't go over because we're going to run out of time. Okay? Are you good? Proportions are not hard. Just remember a z-table. Still adjust. I mean, you have to calculate that standard deviation. Your formula sheet has all these formulas, so you shouldn't ever be lost for those. Now let's look at number 29. We're going to do sample size for a population, okay? Number 29. This one says, a researcher wants to make a 99% confidence interval for a population mean. She wants the margin of error to be within 4.6 of that mean, and they know the population standard deviation, it's 18.22. They want to know the sample size that's going to yield that margin of error within 4.6. Now you have a formula for sample size, okay? You have two formulas. One is dealing with proportions, and this one is dealing with population data. It says z squared times the standard deviation squared divided by e squared. I've got something wrong here, and it's bugging me, so just give me a second to go back. Okay, so here we go. This is going to equal the z squared. I'm going to fill it in down here. Sorry, I was looking for something that wasn't there. I want a 99% confidence interval, so I got 0.99. I'm going to do the same thing. Alpha is equal to 0.01, right? And alpha divided by 2, right? Because I always have to divide alpha by 2 on these, is equal to 0.005. And so I can, from that, find my z-score. Give me a second. Okay. And I find my z-score to be 2.58. Well, it's negative, but I know I only want the positive for these calculations. So next, what I'm going to do is say, I need to calculate, what's the margin of error? Well, they gave it to me, didn't they? They said the margin of error that we want to be between is going to be within 4.6, right? Wasn't that right? That's what I want to be between. And they gave me the standard deviation of the population. They said that was 18.22. I think I've got these numbers right. Yep. Okay, so the only thing I didn't know was the z-score, and now I can fill that in. I've got 2.58 squared times that standard deviation, 18.22 squared, and I'm dividing by the margin of error, 4.6 squared. And this is going to come out to be 104.428. Now, how many people do I need in my sample?
7.
How many people? 105. You must go up. Just put a little arrow beside it. It doesn't matter that it would normally round down, right? How many you need? 105. Okay? Because you can't sample part of a person. Any questions? All right, let's look at one that is a proportion, okay? I'm going to take you to number 33. Now, this is a sample size for a proportion, okay? And 33 says there's a researcher, he wants a 99% confidence interval for the population proportion. The preliminary sample gave a sample proportion of 0.68. The sample size that would limit the margin of error to be within 0.024 of the population proportion is. Now, you were only given a preliminary sample proportion. You weren't given the population proportion. You were just given a sample proportion preliminary, so you're going to have to use that to calculate the standard deviation, okay? you're going to have to use it to calculate the standard deviation of P that you need. So what do I have here? Well, I have a researcher who wants a 99% confidence interval. I'll go ahead and put that down. And then when I know that, I know alpha is 0.01, and I know alpha divided by 2 is 0.005. And since it's proportion, I know I'm dealing with the z-table, and it's the same as the previous one, isn't it? Okay? Both of those have the same one. I didn't mean for that to happen, but they did. All right, so the next thing I've got is he says he gave a sample proportion that was preliminary sample proportion of 0.68. So what's Q hat? If that's 0.68, Q hat is going to be what is it, 32? Right? Go ahead and work as much as you can of it. I know you guys know how to do these because you've had practice already. So if you want to work ahead, feel free. And now I've got my z-score, I've got this, and he had to tell me what margin of error he was working on. He wanted that margin of error to be within 0.024. It's really small, but this is a proportion problem, you know? So he's really saying between 2.4% is what he's saying, right? So I'm going to go ahead with my formula, which is n is equal to, and this time I'm going to say z squared times p, or p hat, that's all I've got, times q hat, and divide it by margin of error squared, right? New formula. What did we do that's different, though? Well, we replaced the standard deviation squared with p hat times q hat, right? If you knew the population, you could use that, but you don't. All right, what do I get? You can check it. And when I have this one, I'm always going to go up. So I'm going to say this is 2515. It would have rounded up, but even if it didn't, like the previous problem, you'd still go up to 2515. All right, so you can do sample size for population data. You can do sample size for proportion data. Those are those two types of problems that you need to work on. And now let's talk about hypothesis testing, okay? Perhaps the most confusing is the hypothesis test, but it uses everything that we have to use. I'm going to go to problem number 63. And this one, the hypothesis test problems generally ask me 3 different questions. You know, what's the critical value for z or t? What's the test statistic value? And do you fail or you reject or fail to reject? Now listen, this is important that you note that because your final exam is worded pretty much the same way. It's going to ask you, and when you run a hypothesis test problem, it's going to ask you what's the critical value, what's the test statistic. The test statistic is the observed value, the one that you got the sample, that sample told you what it was. So what I've called it in all of your videos is observed Z or observed T. That's the test statistic, okay? So critical is the cutoff that we use. That's the where it's going to cut off, and it's going to go either into the rejection or into the fail to reject region. That's our critical value. The observed value is the one that comes along that becomes our test statistic. When we ran and we got the sample, we came up with this particular value for Z. And that's how you know the difference in them, okay? So I'm going to see if I can write this one down for you, if I can. By the way, I use these pages to do these problems. And I'll have some scrap paper that looks like this if you want to work your problems on it for the test. And you can print this off of Blackboard if you want to. So anyway, for 63, if you need help drawing curves, otherwise draw the curve yourself. It says there's a hypothesis test, and the hypothesis it gave us, the null hypothesis is the mean is greater than or equal to 80, and the alternative hypothesis it gave us was that the mean was less than 80. And it said there was a random sample taken of 99 elements selected from the population, and that sample gave a mean, sample mean, of course, of 75.3. Assume that the standard deviation of the population is 24.6 and that the test is to be made at the 3%. Now listen, everything else has given us, it's given us, the other side of alpha. This actually gives you alpha, okay? Alpha is 3%. We don't have to subtract it from 1. In hypothesis testing, that they give us alpha. Okay, so alpha is 3%. Now I have to say, do I have a one-tailed test or a two-tailed test? Because that tells me whether I divide alpha in 2 or not. What do you think? Is this a one-tailed test or a two-tailed test? One-tailed. And which side is my rejection region on?
Right?
It is. How do we know our rejection region is over here? Because the alternative hypothesis tells us. It is, shoot, did I write this wrong? It's on the left. If I wrote it wrong, if I wrote it right, it's on the left. Let me go back because I'm thinking opposite right real quick. Nope, it's on the left. Sorry, guys. There's my rejection. Go to the alternative hypothesis. It tells you, okay? You see it? So in the center of this curve, we've got 0. What are we using? Well, we're using the z-table. Why? Because we have the standard deviation of the population given to us. Now, we've still got to do some adjusting, but what we have to figure out first is what's the critical value for z? How do you know the critical value for z? Well, you got to take alpha. This rejection region is all of alpha. Why? Because it's a one-tailed test. Alpha goes all on one side. This is hypothesis testing is where you don't have a guarantee that you need to divide alpha by 2. In those others we do, but not in hypothesis testing. So in this hypothesis test, we're going to say, I need alpha to be all in one side. I know I'm on the z-table. I want it to be 0.03, and I go looking for it. 0.03. Well, about as close as I get is right here. 1.88 I think is pretty good. Right? And is it negative or positive? Negative. And not because it was on the negative side of my table. I only use the negative side of my table for this test. It's because it is a left-tailed test. How do you know? Look at your alternative hypothesis, okay? Let's see if I'm getting my notes right here. Give me a second to catch up. Okay. This right here is critical z, okay? Just so you know what they're asking for. That's the critical, that's the cutoff, that separates the rejection region from the fail to reject region, okay? So when they ask you for critical z, they're asking you for this. How do we find it? Well, we looked at what alpha was, we looked at what our hypothesis test was, and we found it. It is a negative number because it's on the left side of the test, okay, or left side of the curve. Do you understand? Now, if some of it helps any of you to do this, then learn this. If I have an alternative hypothesis that is less than, then I'm always going to have a negative z as my critical. If I have a greater than, I'm always going to have a positive z. If I have not equal to, I'm going to have both of them. It could be either or, okay? So that should be familiar to you too. All right, so now we've found z. Z is equal to, or critical z, is equal to negative 1.88. Now we're going to go find out where did the test statistic fall. That's the observed value for z. Well, we first have to take this and adjust it. We have to take that standard deviation and divide it by the square root of our sample size. And we're going to go to 4 decimal places with it. What did I get for that one? There it is, 2.4724. And then I'm going to say my observed value for z is going to equal the sample that I took, which was 75.3, minus whatever is in the hypothesis statement, 80, divided by the standard deviation that I calculate. Now, you have to always get this right, okay? It's going to start out with the sample mean. It's going to subtract whatever is in the hypothesis statement, okay? Because that's what's assumed to be the population mean. You understand? We don't actually know the population mean, but we assume it's whatever the hypothesis assumes it is. And then we divide by the calculated standard deviation, and for this one, what did I get for this one? I got negative 1.901. So it would be negative 9.01. This is the test statistic. Okay? That came from the sample. That's my test statistic. So I have two z's, really, don't I? I have the critical z, the one that I says this is my cutoff, and then I have the observed value of z, the one that I got from my sample that actually is called the test statistic. Where does it fall? Is it inside this rejection region or not? Which side of this line, negative 1.88, does that observed value of z fall? Is it to the left or to the right? It's over here. Now, I know that's not accurately drawn, and I'll just go to 2 decimal places. That's where it fell. So, what if they ask you about the p-value? That's the p-value right there, okay? I just drew the arrow. That is the area that is the p-value, isn't it? How do I find it? Well, I go to my z-table and look it up. P-value for negative 1.90. If it was positive, I would simply look it up there too. And I get 0.0287. Okay, that's the p-value. I'm going to put it up here so you know what I'm talking about. P-value is 0.0287, okay? The other test, it failed, it rejected, right? We reject the null hypothesis based on it fell into the rejection range. But the p-value test is always, is p-value less than alpha? Okay? Is p-value less than alpha? Well, p-value is 0.0287. Alpha is 0.03. What you're asking is 0.0287 less than 0.03? And you go, yes, it is. So it rejects. Both cases, they match. They will never not match if they don't match. If you get one says reject and one says fail to reject, you've done something wrong. Okay? You okay with that one? All right, let's hit one of each of the other types. Let's do a hypothesis test. Let's do number 85 in your book. Let's look at the difference it does when it is a sample stand. Yeah.
Will we also be able to run this on our calculator?
Yes, you can. But you will have to answer questions that mean you understand it conceptually, okay? So if you are getting it on your calculator and you understand how and what it's telling you. Another thing I want to caution you about, though, with the calculator is be sure you know that what you're getting is the right answer because it's very unforgiving, you know? All right, so let's look at number 85 while we're in here. All right, it says that there is a hypothesis test with these statements. This one is a proportion. Why am I doing a proportion? Didn't mean to. I meant to do number 82. Can we scratch that out and go to 82? Okay, so 82 says, the company that manufactures light bulbs claims that its light bulbs last an average of 1150 hours. And they have a sample of 25 light bulbs, and they gave a mean of 1097 hours with a standard deviation of 113. I just want to point out how to pick this out of this problem real quick, okay? The company claims is what goes in the hypothesis statement, okay? 1150 is what they claim. The sample 25 gave the sample mean of 1097 and a sample standard deviation. You see it? So we don't have the population standard deviation, do we? We have to use the t-table for this. So there's a consumer group, and of course they want to check and see if the mean produced by the company is less than. All right, so that's how we set up our hypothesis. Hypothesis 1 has to be set to be what the researcher wants to do. And hypothesis 1 says that the mean is less than, what was it, what the company claimed. Now you ought to be able to set the null hypothesis. If this one says less than, and it's always going to say mean and 1150, they have to match, right? Mean, 1150, 1150. The only thing different in the two statements is what goes in the operation in the middle. If this one says less than, then that one says greater than or equal. Okay? Everything else, just do it that way and you won't ever get confused. Now, and then it gave us some other stuff. It said there was a sample of 25 light bulbs taken, and that sample produced a sample mean of 1097. Certainly sounds like they have grounds for saying this. And they gave a standard deviation, sample standard deviation of 133. And they want to test the hypothesis that the light bulb is less than that, and then the significance level is 5%. So alpha is equal to 0.05, isn't it? And do I divide alpha by 2? Well, where is my rejection region going to be? I know it's a t-score, don't I? Because I don't have the population standard deviation. I look at my alternative hypothesis. I meant to give you one that was on the other side, but I didn't. And that's my rejection region. How big is it? 0.05. All right. So let's go to degrees of freedom, what? What's the degrees of freedom? 24. Let's go to the t-table. Degrees of freedom, 24. And let's go to this area, 0.05. One tail curve, 0.05, 24, 0.05 is over here. And I get 1.7109. And I'm going to make it a negative, right? Because it's over here on the negative side of the curve. All right, so now kind of set it up. This is, don't forget, this is critical T, isn't it? That's critical T. That's my cutoff. Now I need the observed value of T. Well, first I got to take and adjust the standard deviation. I'm going to take the 133. I'm going to divide it by the square root of the sample size, which is 25. So it's really 133 divided by 5, isn't it? And that comes out to be 26.6. And then I'm going to say my observed value of T, my test statistic, right? My test statistic is equal to the sample that I took, 1097, minus whatever is in that hypothesis statement, which we're assuming is like the population mean, divided by that standard deviation that I adjusted. And I get a t-value, I'm not sure what it goes to. I got a negative 1.992. You'd probably take it to 4 decimal places. I didn't in my notes, but that's close enough, isn't it? Does it reject or fail to reject? Yeah.
So for the answers for the critical value of T 182, what would the answer be? Since it was 1.7109, but it's only 1.74 or 1.711.
Well, I thought I found 1.7109. Did I not find that on my table? I did? I thought I did. Look at degrees of freedom with me again. Go to 24 and go over here to 0.05.
It is, but the answer in the paper says either 1.704 or 1.7.
Because we went to a different, we had a different publisher at that time. We were using a different t-table. Sorry about that. Thank you for pointing it out. In case it confuses any of you, okay? All right, so here I've got my t-score. I've got my adjusted, I've got my observed value of T, which is going to come right over here into the rejection region. And now, what if they ask me about the p-value for this one? Because this one can be the hard one, right? The p-value for that one, listen guys, if you've got a t-table, you can only use one row on the t-table. You can only use degrees of freedom 24. That's it. We can't do anything else, okay? So what I'm looking for is a negative 1.992, we'll say, and I'm only looking for it on this row, 24. I'm looking for 1.99. Look, it's between, and you just take the positive version if it's negative, okay? Look, it's between these two numbers. What's the p-value? The p-value is between these two areas. Do you understand what I'm saying? We don't have an exact p-value for these. We go between those two. If you're using the table, that's what you do. P-value is between 0.025 and 0.05. Is that less than alpha? Well, alpha is 0.05, so it's between those two. It would be less than alpha, just a little bit, but it would fit. I've got to hurry if I'm going to do a proportion problem for you, so let me do a proportion problem real quick, okay? 92 is the one I think I'm working on. Okay, 92 tells us that we have a test with a hypothesis statement. One of them, the null is equal to 0.26. The alternative is not equal. When you see that, you know it's a two-tailed test. You know you have to divide alpha by 2. When you get the p-value, you know you have to take that p-value and multiply it by 2, okay? That should be kind of familiar to you from what we've done. But you also know you have really big sample sizes, okay? So when I do this proportion test, or proportion hypothesis, what did I say? Which one am I working? 92? What it says is the hypothesis, the null hypothesis, is that the population proportion is equal to 0.26, and the alternative hypothesis is that the population proportion is not equal to 0.26. When I do that, I know I have a z-test because it's proportion. I know I have a rejection region over here, and I know I have a rejection region over here, and I know those regions are equal to alpha divided by 2. Okay, I got a sample size in this thing of 809. Sample proportion that it gave me is 0.24, and it's going to make the test at 5%. Alpha, therefore, is equal to 0.05, and this time I need alpha divided by 2 equal to 0.025. So this area is 0.025, this area is 0.025, and that tells me what my z-scores are. You might remember this one because we've done that a bunch of times before. Let's see if I got over here where I'm going. It would be negative 1.96 and positive 1.96. These, I'm going to say it for you real quick again, these are critical z values. Those are critical z's. There's 2 of them because it's a two-tailed test. So how do I get my observed value for z? Well, first of all, I've got to calculate that standard deviation, don't I? Standard deviation of p hat is equal to the square root, well, now I've got to have q hat, don't I? And q hat is going to equal 0.7, this was supposed to be 0.26, wasn't it? Sorry, and this is 0.74. Okay, 0.26 times 0.74 divided by n. All right, so that standard deviation came out to be 0.0154. I'm going to use it to get my observed value for z. Observed value for z, which is the test statistic, right? Test statistic is going to equal, well, whatever the sample proportion was, which was 0.26, wasn't it? You know what? Brain damage here, because that was supposed to be 0.24. And what I'm using is not p hat and q hat. What I'm using is p and q. Okay? That makes more sense now. Q. Does that help? I am multiplying to get the standard deviation of p hat uses p and q, not p hat and q hat. And like I told you, it gets confusing. Watch your formula sheet for these, okay? So you calculate them correctly. I think I need more cold medicine is what I think I need. But I think my calculations are going to be right because that's what I did in my notes. All right, now, what am I going to do? I'm going to take the sample. 0.24 was my sample. I'm going to subtract what was in my hypothesis statement, and I'm going to divide by the standard deviation I calculated. Basically the same thing, okay? And what do I get for that test statistic, the observed value for Z? What do I get? I have a negative 1.297, or a negative 1.30 if you want, right? What does it do? Well, it's right in here, isn't it? Does it fall into the rejection range or not? You can see it's going to be a fail to reject, isn't it? And it's going to have a p-value that is bigger than alpha. Well, we would have to say alpha, we would have to calculate this p-value right here. We'd find it by going to a 1.3, I can't remember what it is, but I can look it up real quick, and multiplying it by 2, and it would fail the test. It would fail to reject. It should fail to reject. 1.30